Hey guys, Greaves here. Continue on with light, right? And some of the characteristics of light. All right, first, right? Let's just go back a little bit. What is light? Well, it's a wave. Okay, well, for right now, we're going to consider it a wave, right? And we should recall that a couple of things. For an object to be a wave, it has to have a couple of characteristics, right? So what happens with a wave, right? When it hits boundaries, right? So one thing, we get reflection, right? Right? So if you're a wave, right? What happens when it hits a boundary, right? This wave is going to reflect. And we took a look at that, right? So here comes a wave. It's going to hit a surface, right? What is it going to do? It's going to reflect off, right? And we learned, right? We took a look at the angle of how a wave reflects, right? And how it reflects is, right, with something we call the law of reflection. What that states, that is the angle that it comes in at with respect to the normal, that is the same exact angle that it reflects at. So this here is my reflected right? So there it is right there. Okay? So there's one thing that happens if you're a wave. It reflects. It's like an echo, right? If you hear an echo, right? That sound wave traveled away, hit a boundary, bounced back. What else happens? Well, we get some transmission, right? Let's just say transmit, right? So some of the wave will transmit. So believe it or not, right here, this wave that hits the surface, some of it does reflect, but some of it transmits through, right? So that's the second thing that happened. And I just get some absorption, right? So absorbed, right? B, right? Absorbed, right? Absorbed. There you go, absorbed, right? So some of the wave gets absorbed in the medium, okay? So the next part of light that we're going to look at is the transmitted wave. However, I have to give you a little bit of background before we can really talk about the transmitted wave, right? So let's talk about something else real quickly, right? So here we talked about the reflected wave that hits the mirror, comes in, goes out. Now, let's just say that this is air, right? Here's the mirror. This medium, all above the mirror, is air. So bing, bing, right? So the light ray that comes in with the speed of c. Hits this, bounces off, which by the way is 3 times 10 to the 8th meters per second. Comes in at c, bounces off at c. Okay, that's all right. But now look, we all kind of know that there are other mediums out there that light can travel through. For instance, right, if you look into a pool, right, a pool at water, you know that there's water in the pool, and if you drop a ball in the water in that pool, you can clearly see that there's a ball at the bottom, etc., right? So not only does light travel, right, in a vacuum of space, in air, it can also travel in other mediums, like a diamond, like glass. When you go to the window and look outside, right, the light that's outside travels through air, hits the glass mirror, transmits through the glass, leaves the glass, then to the air that's in your house. Okay? So before I really get to transmit, to look at the transmitted rays, there's something that we need to kind of talk about. Right? And I need to talk about what happens when light travels from one medium to another. So what happens, right, to light when it travels from one medium to another? Okay, so what happens? Well, let's take an educated guess. What do you think happens? Well, I'm telling you that light, here's a light ray. Let's just say here's a light ray. There it is, right? I'm going to tell you that this light ray has a speed of 3 times 10 to the 8th meters per second. Suppose I put a big piece of glass here, right? So here's air, right? Here's air. Here is glass, right? I don't know. Big block of glass. Take an educated guess, guys. What's going to happen when this light, but first of all, we know that the light's going to hit this guy and bounce back, but some of the light is going to get transmitted through, isn't it? So here is the transmitted light ray going its way through. Okay, what's going to happen to the speed of the light from the air, let's call this air, to the glass, VG. What do you think happens? Well, if you said it slows down, you are correct. So, what happens to light, right, when it goes from one medium to another? Now, be careful. In this particular case, we did say it slows down, right? Now, for the record, if it's traveling at 3 times 10 to the 8th, that's the fastest anything can ever travel, which is the speed of light. The only option that it has going from air to glass is it has to be smaller than the speed of light. Okay, so I don't know, making it up 2 times 10 to the 8th, something like that, right? So the answer to this question is, what happens when light travels from one medium to another? Well, the answer is it changes speed. Okay, now notice in this particular, I didn't specifically say speeds up or slows down. I just said it changes speed. It could speed up or it could slow down, right? Now, in this particular case, right, when it's starting at 3 times 10 to the 8th, it can just slow down. However, maybe I start in glass. So if I start in glass and I have air over here, what happens to the light when it goes from glass to air? Well, in this particular case, if you said speed up, you are correct. But in both cases, right, the speed changed, right? Went from fast to slow, or slow to fast, right? So we need to talk about this change in speed, and more importantly, how I calculate this speed change. Okay, so what we use to calculate, right, the speed change is something called the index of refraction. Okay, now I'm going to take a look at your reference table, right, and I'm going to give you the equation first. So what is, or how do I describe the index of refraction? N is equal to C over V. Okay, so let me kind of tell you what these are symbolically. So N, what is N? That is the index of refraction. What is C? Well, C is the speed of light in a vacuum, which we know what that value is. That's 3 times 10 to the 8th meters per second. Nothing travels faster. So what is V now? Okay, so this V is the speed of light in a given material. Okay, so now let's take a look. Okay, so first, here is the equation on the reference table. N is equal to C over V. Now, N is just a property of a material. So if we go to our reference table, I think it's on the front page. Where is that? Nope. It's on one of these inner pages right here. There's a rather large chart of absolute indices of refraction. Okay, so let's take a look. Now, we're going to have some numbers. So I want to describe what these numbers mean. Okay, hard to do it here, right, in this environment, but let me just explain what this means. This number is describing how much slower light travels in these materials compared to a vacuum. Let's say that again. This N value describes or tells us how much slower light is traveling in a given material compared to a vacuum. Why is it describing how much slower? Because C, the speed of light at 3 times 10 to the 8th in a vacuum, is the fastest anything can travel. So the only thing that we can really have comparison to is how much slower it goes. Okay, so let's take a look at what that really means. Okay, so air. Light in air is 1 times slower, right? So, okay, by the way, that's not really true, right? it's actually maybe 1.000003 or 8 or something like that. It's a little bit slower, but relatively speaking, as far as we're concerned, it travels the same. But what happens over here? If I'm at air, right, light's traveling at air, and it goes into corn oil, what happens? Its speed decreases by about 1.5% slower. How about diamond? It's going to go from 1 to about 2.5, 2.42 times slower. Does that make sense? So let's think about it again. These numbers are just telling me how much slower light is traveling in this material compared to a vacuum. There is more information here as well, because like I said, we can go from, remember, when light goes from different materials, it changes speed. So when I go from air to corn oil, does it change speed? Yes, it does. Why is it changing speed? Because my index of refractions are varying, are different. So I'm going from 1 to 1.47. I definitely have a different index of refraction, so I have a change in speed. So, by the way, in this particular case, from air to corn oil, since the index of refraction increases, the speed decreases. Is that okay? Now, let's suppose I was in corn oil, and I go to diamond. What happened there? Well, I'm going to compare my index of refraction. Light is about 1.5 times slower in corn oil compared to a vacuum, and it's about 2.5 times slower in diamond. So if I went from here to here, corn oil to diamond, it would slow down again. Why is that? Because diamond has a bigger index of refraction than corn oil. So in these cases, from here to here, slows down, here to here, slows down. Now, what about if I went from diamond to the next one, just ethyl alcohol? Well, in diamond, I'm going pretty slow. What happens to my index of refraction? It's smaller in this particular case. So in this particular case, right, what happens to my speed of the light? It increases. But in all cases, I still have a change because the index of refractions, relatively speaking, between materials are changing. Here's an interesting one. Suppose I was in corn oil and I go to glycerol, right? Corn oil to glycerol. What happens to my speed? Well, the answer is nothing happens to the speed. Why is that? Because the index of refraction, or really how much slower light's traveling in corn oil, is exactly the same amount of how much slower it's traveling in glycerol. So in this particular case, there is no change in speed because the index of refraction is exactly the same. Okay? So I know I gave you a lot of information there, but you can always go back to the video and take a look again, right? So let's try a couple of things, right? Let's see if we can use this to calculate some values, okay? So let's just say I have, and I'm going to kind of make something up. Let's suppose I have water. Here's water. There it is right there, okay? And let's suppose I'm just going to take something, flint glass, just saw it now. So there's flint glass, right? There it is. Right? Let's suppose I have a ray of light. There it is. It's in water, right? And then it's going to go into flint glass. Well, what's going to happen to the speed of my flint glass? All right, well, let's see. First of all, I think I know, right? Why do I know? Because N, I'm going to put a little W right there, right? For water is 1.33. That's from my reference table. What about N for flint glass? And I'm just going to put a G there, right? I think that's 1.66, right? So there it is, right? Flint glass, 1.66. Okay, so what happens? Well, we just reasoned it out before. Since I'm going to a bigger index of refraction, right? My speed must slow down. All right, let's prove it. Let's see. So can I find out how fast light is going in water? Yes, I can. So N is equal to C over V. Now I'm going to put a little W there. And I'm going to put a W there because now I'm saying N of index of refraction for water gives me the speed of light in water. So what do I have? 1.33 is equal to speed of light in a vacuum, 3 times 10 to the 8th meters per second times the speed of light in water. All right? So how am I going to handle this? looks like I'm going to be doing a little bit of cross multiplying. So it's 3 second E, 8 divided by 1.33. And you're going to get, okay, I don't know if you can see this here. You're going to get what appears to be a pretty big number. 2, 2, 5, 5, 6, 3, 9, 0, 9, etc. It is a big number, right? It's a big number because it's still the speed of light. It's still going really, really fast. And I'm going to tell you all these index of refractions are going to give you a speed of light, right? That's going to give us time, an exponent of times 10 to the 8th, okay? So meters per second, so that's the speed of light in water, right? Now, did we slow down? Sure. I mean, if I was in air, if I was in air above water, right, we would be going at 3 times 10 to the 8th. If I hit water, I'd be going 2.25 times 10 to the 8th. All right, so that's how fast I'm going in water. Well, how fast is now the light going in flint glass? Well, N of glass is equal to C of velocity in the glass. So 1.66 is going to be equal to 3 times 10 to the 8th meters per second. And I want V of glass. So let's see what that's going to be, right? Clear that out. 3 second E, 8 divided by 1.66. Lo and behold, remember, you're going to get a big number on your calculator. I'm going to tell you right now, 3 significant digits, and it's always going to be times 10 to the 8th meters per second. So that's going to be the speed of light in my flint glass. Okay? So, what happens when a wave of light goes from one medium to the other? Well, it's going to reflect, but some of it's also going to transmit. But when it transmits, we're going to have what's called this change of speed. I can calculate the change of speed by using a real simple equation, which is the index, right? That's V, right? Index of refraction. Index of refraction is from the reference table, speed of light, reference table, velocity of light, whatever material you're looking at, we calculate. Is that okay? So this is a little bit of, we need this information to really see what we need to talk about next, which is going to be the transmitted wave, and that's coming up next. Okay, guys? See you later.